Today we'll have 2 lectures left, so hopefully in these 2 lectures I'll finish the proof. so I'll find the extent of QL. As before, let's just quickly write down the notations. And my L is greater than or equal to 3. I now take n as square free integer. I mean positive integer. As a set of primes dividing n, and also L division. So in Wells' proof of Fermat's law theorem, the most important thing he proved, or like the most normal thing, at least at that time, modularity. It's so-called modularity lifting theorem. It's the following. Okay. Suppose that suppose that rho bar is an absolutely irreducible representation such that first of all, this rho bar is modular of level n. Suppose that we know that residual galvanization is modular in the following sense, that you can find some eigencurve, eigenform, an eigencurve of level gamma 0 n, such that the associated Galois representation, if you take that Galois representation modulo L, this is the same as the given rho bar. Okay, so you know one lift that can be lifted to a modular form. Secondly, now comes a few technical assumptions. But nowadays, these technical assumptions can be removed. But of course, removing them will take some time, so let's just assume them. Actually, later I'm going to assume further conditions to make our proof a little bit easier. So if I have a prime P, which somehow belongs to the set of ramification sets, and not L, then either rho bar is unramified at P, or after conjugation, rho bar of the initial subgroup is 1, 1 FL. Or yeah, I think the condition was FL. But later on, when we talk about this modularity lifting theorem, I'm going to apply to the case when F is FL. So doesn't really matter that much. 3. This rho bar. So we discussed the ramification away from L. Now I say something about at L. This is so-called semi-stable. Correspond to semi-stable elliptic curves, i.e., this is somehow associated to the L portion points of an elliptic curve with good or multiplicative reduction. So this is kind of a mild way. So basically, 2 and 3 says that in some sense, the way we want, in some sense, this row bar will come from some curve with good or semi-stable reduction everywhere. That's what it is. And 4, the row bar is cyclotron. Then the conclusion is any lift row to catch a 0 of the row bar that is so-called semi-stable. Is modular. I'll explain semi-stable right now. Here semi-stable means basic version of this is that you take the weight delivery representation associated to this representation, restrict to the local dollar group. We know that for the L-like representation, I can always associate weight delivery representation. Even for p-like representation, there's Piaget-Hawkes theory which allows you to associate the corresponding to the weight delivery representation. It's so-called, it's unramified. But with a possibly non-zero n. So basically, the weight delivery representation has two parts. There's a representation and there's n here. It says that how the R is unramified, allowing the n to be not trivial. The Neopolitan operator. So in an explicit way, I guess in this particular case, for typical example, a row comes from like TL over the curve E. Defined over Q with again good reduction or semi-stable reduction or multiplicative reduction everywhere. So that's basically what we're trying to get towards the end. Essentially, so when we study the Fermat's law theorem, we produce an elliptic curve or hypothetical elliptic curve, which will have good or multiplicative reduction. We'll plug that into this theorem. That will be my rho here, where the reduction of the rho bar will satisfy these conditions all these conditions. And the proof goes as I plug in this rho, and I want to produce another rho prime. So this is somehow the eigenform f, maybe f prime, and rho f prime. So starting with rho, I want to convert to another rho f prime. That way, and because rho f prime is modular, so therefore this rho is modular. So that's roughly how the work goes. We'll talk about that part of the proof next time, or that sort of reduction part. So today we'll be focusing on explaining the proof of this main theorem. Still, this theorem is even as stated. It's a little complicated. So I'm gonna in order to avoid some technical issues, for simplicity, I guess, we'll assume the following. Assume further the following condition. I want my rho bar restrict to the local Galois group as above. I guess one was proved that it's super to be semi-stable, meaning that it's either good reaction or the L torsion of the curve with good or multiplicative reduction. I will assume a little bit further. I want to assume that this rho L is so-called Fontana phi. And I want my rho we studied restricted to the local algorithm is crystalline. With quantitative weight. 0 and 1. So this part essentially says that I require my ellipse curve to have a reduction in L. So I basically of course, at the time when Wells proved this, the PID Hall theory, or rather, on this time, LID Hall theory, is developed to the point that it can handle good or multiplicative reductions. But we only have one semester for this course for this topic, so that's trim that part out, the PID Hall theory part out, just to talk about the easiest case. For a similar reason, I want to assume that if P in S and P not in L, not equal to L, so this condition here, I assume that the rho bar is either unramified or after conjugation, this rho bar of the initial group is, the ramification is given by that such. So what we're going to assume that is that if you see P belongs to S, that means that I say, okay, this reference should be ramified at P in some sense. What I want to assume is that if it ramifies at P, then rho bar must also ramify at P. Up to conjugation is that. And I think this will imply that in the Wei-Deligne representation, we associate to any ellipse of this, or any ellipse that satisfies this condition here, this n must be up to conjugation. It's 0, 1, 0, 0, up to choosing a proper basis. Okay, so these are two simplified assumptions we're going to assume to give our proof. So this is so it's typically called minimum modularity. Due to limited time, that's all we're going to talk about. And I'll explain towards the end why such thing will simplify the discussion. And let's make one more remark about the meaning of these two. Basically, the meaning of these two conditions says that, okay, my goal is to show my rho is associated to some modular form. And these two conditions basically says that the ramification of this rho, you already see that in rho bar. In the sense that, see, if rho is crystalline, meaning unramified for the LID version, then the rho bar is unramified, of course. And this rho in the generified rho restricted to Gauss group of QP is, if there's a monodromy n here, I kind of already see that in rho bar. 1 FL01. FL is not 0. So sometimes the ramification, you already see that in rho bar. So that means that as you deform, you don't include further ramifications in such deformations. This will result in the corresponding deformation space we discussed in a minute, or at least the local deformation space are smooth. So that's the advantage we're taking home. You don't allow this. Sorry. True said this. The second condition, you don't allow the rho bar to be unramified. if rho is ramified, then rho bar has to be ramified. That's what the condition says. Yeah. So the thing is that if you allow rho bar to be unramified, this will be your final exam problem. If you allow rho bar to be unramified, yet you allow your rho to be ramified, so there are basically this rho bar will have two deformations. One deformation will deform into something which is ramified. The other deformation will deform into something unramified. One ramified deformation, one unramified deformation. So there are two components here. You have to think where your rho lies on, which component you're on. Maybe the initial seed data f prime is on one component, and your rho is on the other component. So you have to find a way to go from one component to the other component. That's more difficult. If you know your rho bar is already ramified, you cannot deform into something unramified. So there's only one component. So you know that your rho and rho f prime will be on the same component. And you can say, okay. So I added these conditions to make sure basically the local deformation rings are nice. As we'll state. To properly state that, we need a little bit more notation, unfortunately. For each place, I want to set a so-called deformation condition. That's to say that in other words, I want to say, for those primes in the places where allow ramification, that's different from L, I'm going to write R rho bar P, meaning that restriction your rho bar to P. Frame deformation, but I want to put the local condition dP here to mean deformation framed. With QL bar points X are the representations for which corresponding weight Deligne representation of this rho bar is unramified. With n equals to 0, 1, 2. Okay, I'm deforming my rho bar to something which is ramified. So that's my component. And we know that this is a quotient, the usual quotient of this R rho bar, right? So, because how I define, maybe let's also fix a determinant for which this, and also determinant of rho x is just a cyclotomic character. So let's not write cyclotomic. So this is already contained in what the deformation condition is. Okay. So when I write this, I mean I already fixed the deformation so that it deforms to something with determinant being cyclotomic character. And this is, and one can compute in this case that I should have left this as an exercise, but anyhow, I was a little lazy. So this deformation ring for this one is precisely 3 variable power series. So as Yuanyang just asked, if this rho bar were an unramified deformation or an unramified representation, and you cannot. So in that case, you cannot quite put this condition here because that's not a closed condition. You will have an open part. If you want this rho x to be precisely this part non-zero, if you want some polynomial operator where this number is non-zero, so that's usually an open subset of your deformation ring or a spec of deformation ring. So that's an open condition. So so that's very bad to work with. So in that case, you have to consider deformation which are unrarified with this being 0 or not. So then you have to that's that. Okay. So that's one thing. Secondly, if P equals to L, crystalline deformation. So again, the frame deformation has a natural quotient, which is, I take those which deform to crystalline representation with hard K weight 0, 1. I'm going to write that as rho bar L, DL, sorry, frame, DL. I should have just removed the frame. So, by our dimension, so, okay, maybe I should say Y3. So that's because the dimension of H1 of the local Gauss over here for this one, I equals 0, rho L, this is circuit. Okay. So that's because the local dimension of this guy is precisely governed by H1. And there's no H2 basically in that case. And similarly for this one, I mean you add a little bit of condition. Maybe I should say add some conditions for dp. Oh, sorry. And for this one, we talk about, so roughly speaking, this dimension, roughly speaking, should be equal to, I guess, the dimension of SLN plus a little bit of a dimension of SLN modulo the Bn. So this comes from the framing, and this is sort of essential dimension. So it's SLN modulo the max. So whatever the quotient dimension is. So this is 3 plus 1 equals 4. I think I said it somewhere in the recording. And the essential dimension of this deformation, relative to O. So this relative to O has dimension, roughly speaking, dimension of SLN. This gives you the framing of PDR. That gives the framing, and this is the essential dimension, which is dimension of G mod B. Likewise, the 3 and 1. And so therefore, in this case, it's O Y1L, 2L, Y2L, Y4L. Because all the Fontana-Phi deformations will give you a power set. And also, we computed the deformation at infinity. So in this case, one of the conditions that's hidden in the theorem, which is determinant rho bar being cyclotomic, this will tell you that determinant rho bar, the compact conjugation is -1. So the two, for me, the eigenvalues are plus, the two eigenvalues of the compact conjugation are 1 and -1. In this case, deformation, so I don't put any additional conditions on it to make my notation a little bit more uniform, so I still write that infinity. In this case, this is isomorphic to, not so this is 2-dimensional. We did this computation, I guess, for a little while ago. Okay, so this 2-dimension comes from, so you have two eigenvectors, one for eigenvalue 1, the other one for eigenvalue -1, and these two variables come from somehow choosing your two eigenvectors. Okay, so that's the benefit of choosing my additional sort of hypothesis that these deformation rings are just power series rings. That's nice. So in general, of course, if you work with Wiles condition, these deformation are not as nice, but they are still somewhat workable. So semi-stable. Those are semi-stable rings. You can still work with a little bit work to do. Not a little work, somewhat work. So now let's go back to the basic idea of Wiles' proof, which is that remember that we can associate. I define R rho bar D to be the deformation ring. For rho bar with these local conditions. So namely, I only look at those deformations of this rho bar where a place that I want it to be ramified, it only ramified in a way that somehow the weighted ramification is, the ramification part is unramified, where you possibly have an end, or actually you have an end. And where at P, you don't allow it to ramify, so you get crystalline deformation. So work with that. Now modify a little bit of what we said earlier. So earlier we did consider the module space module forms, and I can localize the Hecke algebra, and I make some idea of the Hecke algebra associated to this rho bar here. And this one, of course, is acted out by the so-called Hecke algebra, right? And we'll have a mapping to this Hecke algebra. Let me call it the usual deformation ring, right? The sense over here, the trace of provenience at P to the TP operator. Maybe I should start here because I don't want the Hecke operator at the dividing end to get involved. So the trace of provenience inside the universal deformation ring will map to the Hecke operator action. But we know that all the representations with QL conditions here do satisfy these conditions we have here by the properties of the form that's associated to these representations. So therefore, this will factor this will factor through my conditioned deformation ring. The reason I want to work with this is that this is a much smaller ring than that one, and it's more tight. Or basically, if you think about the other way, sorry, another way to think to say this is that because the deformation ring acts on this space, will make this space the module over this deformation ring. Then what I'm saying here is that the space of module forms is a module over this deformation ring, and the support of it is contained in the spec of R rho bar D. So the support of the module lives in the deformation space. In fact, the deformation space should be, in this case, sort of two-dimensional, relative two-dimensional to the base. And there's space module form was supported on one-dimensional subspace. So excuse me, a zero-dimensional subspace. I don't know how to say it. Supported on a very small piece of it. The dimension difference is mostly because of the crystalline condition. In some sense, because we know that all the representation associated here is crystalline at P. So therefore, the associated representation will always kind of be somehow crystalline at P. And therefore we will always sort of lie down here. So I can pin down where exactly the space module forms lie on over here. And I'm gonna, in a very mild way, correct a small error I had last time. That last time I talked about, I was talking about module forms, but better, especially talk about the dual of this module form. It's just when you patch, I guess it's more natural to patch the dual module forms as opposed to the multi-space module forms. So this is the half of this S2 into O. Doesn't change much. Doesn't change anything except one. But it just more makes the patching more canonical. Of course, it's already quite canonical. So now, under the if we somehow think of this picture this way, that the space module form is a module over the deformation ring, then the given representation rho is a point. Maybe I can say it's a Q L bar point of this deformation ring, or maybe speckle. So because rho bar is a lift of rho, rho is a lift of rho bar, and therefore this will define a QR bar point of speckle rho R rho bar D. And therefore, so existence of an F such that rho F being the same thing as rho, that's equivalent to say that if you look at the support of this module, supports of the spatial module form, this contains a point, let me call it X rho. Contains a point X rho. Let's draw a picture which I will use later. So, kind of drawn before. Not quite done. I'll go back to that. Anyways. So let's draw the picture this way. I'll try this way. Right. So I'm drawing a speck of O vertically for some reason. So this is the generic point E, and the special fiber, special point F. So this is a special point. This is a generic point. And what I'm describing here is speck of R rho bar. Okay. So what it looks like is that in fact the correct way to think of this is a relative dimension 0 to O. So it's going to be something supposed to be finite over O. I think it's true, but I'm not so confident in general. Okay, so this will look like something like that. So it will parameterize all possible deformations of this rho bar to characteristic 0. Maybe there are 3 deformations. So rho 1, rho 2, and rho 3. Okay, so this is the deformation ring. And I have a module over this deformation. I mean, my spatial module form will be an O finite rank O module. Carries an action of this finite O algebra action. So therefore, that can be reviewed as a module over the speck of the thing. Maybe somehow the known condition, or the given condition is that maybe one of them is rho F. Fine. Remember, in the modularity lifting theorem, there's an initial data that your rho bar is congruent to something which is modular, say rho F prime. So we know that the support of this space module form at least contains this branch of this information space. But typically, my rho is in another branch. I want to show that somehow the other branch is also covered by the spin monopoly. Or rather, basically, I want to show all the branches covered by the spin monopoly. So I don't know where my rho is. So that's what modularity lifting is proving, is that if you know one of the components covered by spin model forms, then all the components are covered. So that's what I'm saying here. So I need to prove. I need to prove that basically support of the S2 of this thing is the entire set. Basically, there's no other way. So somehow you know somehow to prove that knowing this null is empty, you have to show this is everything. That's it. So at this moment, I'm drawing this in such a figures way, but it's also possible this is also deformed in the purely characteristic zero. It could be purely characteristic alpha. Some sort of vertical direction. That's possible. Technically possible, but I think it's not happening. So that's the goal, or rather, somehow this is a reinterpretation of Wiles' theorem. So Wiles' idea is to relate this past to a local question. In other words, somehow the global deformation rings is very difficult to control, whereas the local deformation rings are much easier to control. So Wiles' idea is let's pass to a local deformation. Let's see how I'm going to write this. So in order to pass to a local deformation ring, I want to sort of recall. So one of the issue is that this ring here. So there's a small problem. Is that there's no map from R rho bar D to this R rho bar P, or rather frame DP. Somehow, oh, excuse me, the arrow goes the other way. I'm thinking about that. Okay, there's no map going this to here. The reason is that for a local deformation ring, even though the global Galois representation is typically absolutely irreducible, but when you restrict to a local Galois group, it's typically reducible. It's typically direct sum. Basically, our assumption is that rho bar restricted to the initial subgroup is reducible, and basically that says that your local rho bar is reducible, not irreducible. So therefore, this deformation ring is a little bit questionable. You have to put frame. But if you put frame, then there's no map. These two. So therefore, you have to put frame on the global one. That's what we did earlier. So we consider this R rho bar frame at S of D. So this is this global deformation ring. Oh, sorry. One more thing. Oh, I put a D here. Okay. When I put D here, I mean also I require the determinant taxonomic character. That's already kind of close. Okay. Global deformation ring with two things. With local condition, I specified D and frames at S. So we discussed this thing. So it's basically set to all the rows and all the H V or V and S. Where rho lists rho bar and HV belongs to PTL. Okay. then when you map, you conjugate your rho by this HV. And up to equivalent. Remember that. And there's a natural maps. I still like to, I know I still like to think of this sort of geometrically. So let me say these are all affine maps, affine schemes. So that's okay. So there's a natural map from this to each of the local frame deformation. Because V stands for both finite times and Archimedes. Okay, so this is maybe that's the same thing as spec. So maybe I should write both. So this is both. These are all affines. So basically, we're talking about ring map between rings. Okay. So the spec of all the tensors of B and S are rho bar B. Right. B. So in terms of, I want to say, okay, there's a local deformation ring mapping to these. So this deformation ring, I'm going to call it R loc. Right. Okay. So this way I relate the global deformation ring with the local deformation rings. Now I'm gonna. So that relates to rings, but then my module doesn't quite pass. Module is still a module over this one. Another thing is that this. Hold on. Yeah. So this one also so somehow because this is a formal power assist ring. So we also said, I guess when we discussed this. Also recall that this is isomorphic to the one without the frame just by putting a bunch of framing variables. So you put a bunch of sort of dummy this HVs, they don't really play much of roles. In fact, you can write this as a formal power circling. Which variable did I use? X. So for each of the S you put in, you get three sort of three times that. So each of the framing you put in, you get three sort of choices. In a sense, sort of 3 is really n squared minus 1. So PDL n is PDL2. So basically, this R rho bar D take care of the rho part. The HV part is sort of you can take freely. So you see PDL, you're in PDL2, so you have essentially three places you can move freely. So you have a power source like so. When writing like that, so I can define a framed version of this, so S2. So these variables, xi, they're called dummy variables. In the sense that they don't really play any sort of essential roles. They're just added in so that I have a way to map these things. But they don't play any sort of essential. There's no essential content to them. You can put them in as you want. So I want to define the S2 dual with its framing to be just simply the tensor. Sorry, this is no frame. Frame S. So what this is basically, you have this thing and the basic tensor are formal power series. And once you've done that, so this will carry an action of R rho bar R frame. And therefore your local deformation ring will be able to act on it. Not something. the local deformation will be able to act on the specific order forms. Oh, maybe I should put a D here. We're imposing local conditions. So, our earlier theorem says that this global deformation with local frames as a relative representability. It's a relative deformation ring over local deformation rings. So it's represented by, it's generated by R elements and quoted out by R relation for some R. R is, okay, perfect. Some sort of some complex component. And it turns out the H1 and H2 have the same dimension. So this comes from the H2, and this comes from H1. So we calculate that somehow the H1 and H2 have the same dimension. So last time, okay, not quite last time. We also let's auto recall by Chebyshev density theorem, essentially for each. Later on, I call it M. There exists a collection of primes, so-called Taylor-Watts primes. QM. Such that each QI M is common to 1 modulo L to the M. I'm gonna just for simplicity, I'm gonna assume that L to the M exactly divides this. This is the easy fix if that doesn't happen. If it's not, it's divided by higher power. If that doesn't happen, and then I'm gonna write delta Q, or maybe actually I wrote this. So this LMI divides that. So this is the same thing as product R of V mod L to the MI. This was the delta. And secondly, rho bar of Frobenius of QIM has distinct eigenvalue. Thirdly, let me finish this third. Remember that we have this deformation ring, so it's a quotient of our rho bar ring as here. But then I can also talk about deformation, where I not only allow ramification at S, but we also allow ramification at additional Taylor-Wilds types. So that's I'm going to denote by S union QM, or maybe QM. This is the allowing ramification at QM. The essential condition is that you can somehow, there is a factorization that's this surjection here. So this one is also generated by precisely n r elements here. And also at the same time, let's recall that this one has a essentially I want to write O here because they have just sort of dummy framing variables with many sort of not interesting framing variables here. And the relation between this deformation ring and this deformation where you allow this ramification is that over here you can put in the group algebra QM and then I put in this framing variable. Mod augmentation line. So in some sense, this group algebra delta QM precisely corresponds to the image recognition W. When you quotient that out, it becomes a deformation ring where you don't allow ramification QM. Okay. I'll stop here. These are just basically recollections of this, of what we talked about. And now, for the next hour, we're going to do all logic. Oh, no, for a little bit, and then we'll do logic. So that's all good? So now let's go back to the question we had earlier. So we want to, okay, we'll have this deformation ring. Okay, and we know some components sort of modular, red one. And I want to know all the support of the space module form. Let me just write space. Oh, that. I need to put a dual here. Okay. And I want to say the space module form has full support on the deformation ring, or spec of deformation ring. In order to do that, what we're going to do is, well, first of all, it's equivalent to talk about, I put a frame on here. And similarly, I put a frame here. And again, I want to show full support. It doesn't change anything. Because everything's sort of formally smooth, so that's okay. So the idea is that I want to eventually get to here. So this ring here, this frame deformation ring, is a quotient of R log frame D. See that this deformation, this ring here is a quotient of this with the form of some variables. And this is a very nice ring, if you remember. So this is nothing but the O of a bunch of variables. With this sort of Y, okay, so this Y1, sort of L, this P, all these things. Anyway, this is the formal power system. Now we're going to dream. Now suppose that we're in this situation. Now, suppose my deformation ring is just like this, kind of a formal power system. That's kind of nice, right? I mean, you have the row bar here, and you have sort of a whole bunch, which is all connected. And if you know that one piece inside of that is modular, and if you know on the other hand the space of modular form is large enough, then it must be full support, because this guy is irreducible. There's only one component here. It has to be everything. So know that if one component is modular, then all other components are modular. So Wald's idea is that he wanted to move this situation where you have multiple irreducible components to the situation where you have only one irreducible component. To do that, so he needs to do some he needs to use these Taylor-Wiles pipes to make this a larger. So this increases into rho bar QM. So therefore, if you allow some additional ramifications, still you start from the same rho bar here. Try to draw this picture. Okay, this was your red. This was your red component, which you know to be modular. But then because you allow additional ramifications, so you might grow more sort of ramifications. That's sort of more components which are regular. You have more lifts to capture zero. You allow more ramifications. And this would correspond to over here, S2 of this thing, intersect with gamma 1 star QM. And they localize M rho bar prime, double prime. So this spec goes this way, but this module surjection goes. And this is not growing in a random way, but also in a more systematic way. So over here you don't do anything. So this is basically a spec of all. And you already in this frame, so I record the frame and put it in. But then, as this diagram over there shows that spec of O of delta QM. So somehow the original picture is a Cartesian pullback of this picture where you allow some ramification at these Taylor-Wiles times. This is the Cartesian. But the benefit that you are growing, but the benefit that this is still sits inside this sort of big envelope we're talking about. You're growing inside this big envelope. I don't have another color. Somehow you should think that there's always kind of a big envelope. Here, you're growing inside this envelope. Okay. Now, supposedly, now you want to take limit. Now you get to, in the limit, you get to some S infinity. Maybe S infinity or so that's the limit of these spaces of modular form when it takes over the limit. And then this in the limit, this will, well, I'm not quite sure the deformation ring. I mean, suppose it's going to fill up the entire space, but we don't know yet. I mean, it will fill up something. But on the other hand, I know the bottom thing does fill up. Because, let's write these dummy variables here. And what is this delta QM? Well, this is a group algebra of a, so let's do the calculation somewhere. Okay, fine. So what is sort of O of, say, Z mod L to the M? Right? So these delta QMs are sort of group algebra of these type of meaning groups. This is just OZ, is a constant, right? So this is E to the L to the M minus 1. Right? May as well just change the variable Z into Z plus 1. Okay? So then you know this thing looks like Z to the L to the M plus, I don't know, high power, I guess. I don't know. And there's also L times, whatever that is contained in some sort of L comma Z to the M somehow. But as goes to infinity, somehow the limit of this one will become, somehow taking limit. Sorry for writing very non-mathematical. Right. So let M go to infinity. that's equal to inverse limit of this m go to infinity. So that's the same thing as O double bracket. Okay. When it takes over the limit, it becomes, so one of these factors becomes O double bracket Z. Now this, you have how many R Taylor-Wells primes? So call it Z1 through here. So in terms of, you start with sort of a single tree and you grow them into kind of a whole bunch. Okay. And what happened? There's additional thing that's happening, which is that as you grow from a space of module form here to say QM level, the space of module form Y2 is a finite free module over this one. So this is finite free. So this one over here, this is finite free. This one of the conditions I think I said last time. And as you take a limit, because each time you kind of have a Cartesian thing, so therefore this thing is also finite free over this space here. Once that's done, there's in community algebra there's a theory called depth, and we'll say a little bit next time. But basically, the meaning is that because that module is finite free over this full power series of what, of how many variables? R plus 3 times the number of points and primes in S. So I don't know. So let's say R plus 3S. So you have something which is finite free over R plus 3S variable full power series ring. Whereas this one, this local deformation ring is also a formal power series ring. Like you count the number of variables. So the Y has R variables, and that means these local deformation ring variables are precisely 3S. In R plus 3S variables. In other words, this ring and this ring, they're in terms of size, they're roughly the same. So therefore, if you have a module over the smaller ring, over the bottom ring, which is sort of finite free, so that module roughly has some size definition, whatever that means, R plus 3S. So it must have the support of that must be also of roughly that much size, like R plus 3S. So therefore, it must be support. So if support is not empty, then it must be closing. So then you go back to show that it must be full support over here. That's the rough idea. Okay. Any question about this rough idea? So you start from the very basic case, and you grow to the infinite case. The ring becomes easier, and then you can show the full support. Except there's a big problem. There's no inverse system to take limit. Except there's a gigantic problem here. Is that, okay, you fix an M, you choose a bunch of prime. Right? You fix an M, you choose a bunch of prime. But for a larger M, these bunch of prime you have to change for a different set of primes. There's no way you can choose R prime that works for all M. If you choose different primes, these R rho bar QM, they're very different from each other. There's no map between one another whatsoever. Right? This allows verification at these primes, and the next one will allow verification at other primes. So there's no relation whatsoever. The space is the same thing. There's no inverse system. So that's the biggest problem in the sense that it's a very nice idea, but somehow there's no inverse. You can't take limit. So there are two solutions to this. Essentially one solution. So there are two versions. The original version was due to Wiles. Wiles' idea, here's basically what's the slogan, is that here's what basically he used. A sequence in a compact space. I don't know, compact household? Household? Maybe? I can't remember off the top of my head what this could be. some nice compact space has a converging sequence, subsequence. Compact subsequence. Maybe add some of the more condition. So, okay, you have a bunch of points. Sometimes you think of these different apps will give you some infinite many points on whatever space of all possible configurations. You can always find a converging subsequence and take limit of that. Okay. And another version. So this was later on, in terms of writing, simplified by Shota. He uses so-called ultra filter, which is basically essentially the same thing. But then when you write it, it's a lot more elegant. So we'll introduce the second method. Next 35 minutes will be a crash course on ultra filters. It's a really fun exercise to do all these questions. So this machinery will give you a way to take limit where you can't take limit. I mean, the theory of ultra filter is kind of Asian. It's kind of Asian theory. It's known like maybe 50, 60 years ago, way before Shota was born. But he uses to simplify whilst writing. So here's the definition. So let S be a set. An ultra filter is the following. Is a set of subset. It's a collection of subsets of that. To tell, first of all, empty set is not enough. Secondly, if a subset of S is in the ultra filter and you have something which is bigger than I, then the bigger one, the bigger set, lies in the ultra filter. So ultra filter contains always large sets. Certainly. But if you have two subsets, their finite intersections belong. So this ultra filter is closed under finite intersections. Fourthly, and most importantly, is for any set, exactly one of I and its complement belongs to. Okay. So basically, ultra filter is a way to separate all subsets of S by in F or not in F. And those are in F. If something is in F, then anything larger than that is also in F. And if something in F and another thing in F, the intersection is like intersect to reflect on this. Example: for any S in S, if you have an element in S, I can define ultra filter. Of course, a not interesting one. All the subsets I in S containing S. Let's call that principal. Really principal group. Well, I erase board. You can check that. Extend all these four properties. Notice these are the ultra futures that we're not interested in. I have another line. If I know that if a singleton belongs to this ultra filter, so namely if the singleton is selected, then basically by the second condition that if a singleton is considered, it's contained in that, then any subset contained in S will be selected into this F. So therefore, basically, this F has no choice. So F must be Fs. Again. So basically, if F contains a single element, then it's not very interesting. Singleton, then that's very interesting. So here's a fact of your lemma. If S is infinite, we only use the case where S is n integers. Then I can always find non-principal ultra filters. One thing I should point out is that for such F, for non-principal ultra filters, the subsets that's sort of in F, they have no common element. If they have a common element, if they have a common element, they will become this type of thing. So let's give a really quick proof. Basically, start with so-called cofinite. So that means that first of all, I know that if I take all the subsets which are complementary finite, or the complementary sets are finite, then they would satisfy the first condition, no problem. Second condition, no problem. Intersection, no problem, except for 4. So we'll satisfy 1, 2, 3, but not 4. And so there are also sort of in between subsets. You don't know whether it should be belong to F or not. And for those, use those ones. Use those lemmas. You have to start starting from a cofinite. Those are called filters. Set by 1, 2, 3, but not 4. And somehow take a maximal chain and find under solution. And the maximal, or the maximal element is in the chain will automatically satisfy 4. Just standard things. Say the details. You can think about it. So let's discuss a few basic properties so that we understand this ultra field a little bit more. So first of all, if my S can be read well, if I have a partition of the set S into sort of n pieces, n subsets, disjoint union, then exactly one SI belongs to. So in particular, if S is finite, this will tell you that exactly, if S is finite, I can write this as a disjoint union of singletons. Then exactly one of the singletons must belong to F, and all the ultra filters by definition will be symmetrical knowledge. Well, let's see. Let's prove. So let's separate this way. So this versus the rest. Okay. I guess this is just S1 complement, right? So by 4, exactly one of them belongs to F. Okay. I first ask whether S1 belongs to F or not. If it doesn't, then the complement belongs to F. So let's separate the two cases. So if S1 belongs to F, then I claim other Sj can't belong to F. Otherwise, but their intersection is the empty set must belong to F. Why? Intersection with what? 3. Right. If you have a set belongs to F and if another disjoint set, if both of them belong to F, then intersection is empty belongs to F. So this will be with the first problem, with first condition, the empty set is not. So okay. So therefore, basically, if S1 belongs to F, then we're done. Exactly one S1 belongs to F. Otherwise, we know that this S2, this belongs to F. And then I can look at S2 union versus S2 complement. Oh, maybe I can write it more efficient. Okay, I can look at S2 versus S2 complement. If S2 belongs to F, we win. Otherwise, right? Otherwise, S2 complement belongs to F. Okay, and you continue that to ask that for each of the n sets there. Right? If one of them passes the test, then that Sj will be the unique element that belongs to F. If all of them fails, if all Sj does not belong to F, then I would say that all complement of Sj belongs to F. And then the intersection of all of them is precisely empty, so that's in F. Again, I got a contradiction. I should have did that. Should have done that. Okay. That's good. So the purpose of talking about these properties is not to try to prove them, but rather somehow get you familiar with how the ultrafilter works. It's okay to go some roundabout. That's one. Secondly, if I have a subset, that's it. They can restrict ultrafilter to the subset by taking all those J's in F, then intersect with R. Because this is ultrafilter. For I. And one thing you know that is, okay, you take any subset of F, any J in F, intersect with I. But this thing itself also belongs to F, because I is in F by the property that ultrafilter is closed under intersection. So this is also the same thing as saying that all the J's in I such that J already in F. Give me the same thing. What do I need to prove? Well, let's sort of try to remind ourselves all the conditions. Empty set, not in here. Second property is if one of them is bigger than, if I is bigger than, if I prime is bigger than I and I in F, then I prime is also in F. That's okay for this one. Right. You have sort of a big upper bound. So second condition is okay. Finding intersection seems to be okay, because finding intersection works for F. It's basically only the fourth condition. We have to check. We have to check that somehow for any J, J is exactly one. J and I, J already in I. J and I deleting J belongs to F. Yeah. Right. So let's, I don't know, say J is not. I mean, these two can only have at most one belong to F because they're intersecting at P. Already kind of proved. So if J does not belong to F, then this will tell you that J complement in the larger space belongs to F. In the S belongs to F. Then I will say I intersect with JF belongs to F. And this is precisely I. My understanding of teaching this part is that I think the best way is to just stop the lecture and let you just read off. I think that's the best way. Everything's sort of very straightforward. 3. Anyway, let's see what we have to lecture. An ultrafilter. F is non-principal. If and only if it contains the cofinite computer, this thing I discussed. All subsets are complementary finite. Cofinite. So proof is F is non-principal. We show that that's equivalent to say for any S, the singleton does not belong to F. Or in other words, the complement belongs to F. So now basically by the intersection property, the complement of all the singletons belong to F is equivalent to saying that F contains all the cofinite. So I'm done with 3 properties. Any questions about it? Okay, so now I'm gonna feel like this part of the discussion is very detached from the earlier module 4. So now let's sort of make the connection a little bit. So now I want to, for the rest of the lecture, I'll take S to be the inset of integers, and I'll fix F a non-principal ultrafilter. I'll define so-called ultra product. So okay, it's given A a collection. Maybe. You know what? I've decided I'm going to call it ultra limit because although other people don't call it this way, I think this is really just a limit. Let me call it ultra limit. Other people call it ultra product. Because what we're doing is really taking limits. We'll see that. All we're doing is really taking limits. When writing this note, I've been thinking whether I just change the name to just ultra limit. No, it's not that. So I have a collection of non-empty sets. So I can define a so-called ultra product with respect to this ultra filter to be the following. First of all, you take the sort of the naive product of all the sets you have, and I want to quote it out by some relations. If you have a collection of AN, that's equivalent to another, sequence AN prime. If and only if I'm going to write it AN F AN prime. So I'm going to read. I'll define what it means in a minute. I'm going to read this as AN equals AN prime for F many. Somehow they're equivalent. You don't have to require them to be equal for all n, but only equal for f many n's, in the sense that this means that you can find a subset such that an is an prime for all n I. Two sequences are the same, or consider the same, if they are the same on a lot of terms. A lot meaning that it's determined by what the ultra filter says. Ultra filter says, okay, a lot means that. So see that this ultra filter don't have. You can show that the ultra filter they don't have. Okay, I guess put it this way, because these non-principal ultra filters, they contain all the cofinite subsets of n. So therefore, all the finite sets are not in this ultra filter. So you have a sequence. You only have finite many places to be equal to another sequence. They're not considered the same. But if they are equal at sort of infinite many, and those infinite many are precisely a subset of f, then you win. They're the same. Okay. So I was gonna suggest to write limit f, but that's what really it is. You'll see. So first of all, if I have a subset in f, then as I discussed earlier, that I have a ultra filter for this subset I. And similarly, I can form a sub-collection. I guess maybe I should say that for the ultra product, I don't need the set to be n. Right? I can take it to be any set. Okay. So then, I can form ultra filter with respect to this sub-collection. AI. And that's the same thing as ultra filter. It's something I forget about. Lots of terms in the product. I still get the same thing. The map is just the same thing. This is what you think it is, basically. You take a sequence to be a sequence where the AN preserves, and the BNs are EM column for your favorite EM. Doesn't matter. Anything. You take any map, it will be the same map. That's because you can take it as you want, but that is also the same thing as F. In terms of F equality, that's sort of the same thing. Because they are equal on all they're equal for F many n's. Because they're equal on these i's. This I is a subset we selected for that. And they're equal here. I don't care about the rest. Take it out. So basically, if you know what's happening on this I element here, that's enough. I don't care about it. The rest doesn't really matter. By equivalence, all those are equal. Can remove finally many AMs. Because I can take my I to be any sort of co-finite subset of n to remove all these things. Essentially, majority wins. It's like both majority wins. So that's one. Okay. Two. Assume that all ANs are finite sets, and their cardinality is uniformly bounded. By some big integer n, then I can compute this ultra product. This follows. So let's make a computation. So step one. So this will give you a way to compute. I mean, we're only going to be used in the case where an is uniformly bounded as sets. So let's compute. So I want to group these ANs by cardinality. So I'm going to write n to be, these are all non-empty. You're not allowed to take empty sets. So I can write the set of integers as disjoint union of I1 through In, where IR is all the integers such that the number of elements in AR is all the integers in N is R. And by the basic property of ultra filter, you can find a unique IS, a unique S, such that IS is in that. I make my set N into a disjoint union of such bunch of finely many subsets. Then our earlier property for ultra filter is that exactly one of them belongs to I. So I have some IS. So then, if I make the ultra filter, that's the same thing as making an ultra filter which sticks to this IS of AIS. I will just discuss. So basically, those factors with wrong cardinality are thrown away. So that gives a way to pick out the right cardinality. Of course, when you change for a different ultra filter, it will give you a different answer when you take this product. That's another weird thing about this table. Okay, step 2. Now I'm going to do a brutal thing. So I want to define an A to be an abstract set. And fix arbitrary bijection from A to AI for each I in IS. I mean, these are all, I'm talking about set theory. So all of them has cardinality S, so I can identify with some abstract set with cardinality S, no problem. Then, this ultrafilter product is just A. Basically, I want to show that ultrafilter product is not large. Set into the sequence using this abstract icon. Basically, the idea is you do whatever you want. I guess I have to prove surjectivity, right? I mean, the injectivity is kind of clear. Yeah. The injectivity is clear for different CJ. So when you map CJ over the right. So now, suppose I have a in the product of this AI. Suppose I have a sequence. Then I can rewrite this set IS as each union of the following. Okay? I'm going to call it ISC1 to ISCS. These sets are determined by whether it looks like whether it looks like C1 or C2 or CS. Where ISCJ is all the indices I such that AI is psi I CJ. Given a sequence, if I give you a sequence, and I want to know, okay, which one does it look like? Which CJ does it look like? Then of course, different components will have different opinions. So you have to serve. As different opinions, but on exactly one. ISEJ belongs to F. The F is kind of a dictator that shows which one is the correct answer. Then this will tell you that AI will be F equal to that sort of BICJ. So I want to convey the idea that somehow the ultra, in some sense, UFA is somehow a universal way to do this. I don't know how to say it. Or maybe either for different apps, we'll give different ways to take limits. And for all possible maybe write it this way. So for all possible ultra filters each ultrafilter gives you a way to take limit. In some sense. For different ultrafilter, you have different ways to take limit. And each filter, especially at each of the places, tells you that which majority is more conscious. Okay. So 3. If ANs are algebraic objects, for example, rings or modules, so is the ultrafilter, like ultraproduct A. 4. Well, let me, anyway, I'm already here, so let me just talk. I'll be running over time for a few minutes. So if R is a finite local ring, and set, let me try to be able to distinguish the two. So it's curly R. Let me run over. Then each ultrafilter will give a homomorphism from this R to, of course, a ultraproduct of all these, the constant ultraproduct, which by our step 2 here, we're setting the ultraproduct just R itself. I mean, I take, of course, R being identical map to each of the components, so that it's the constant. Let me call it. And of course, I said R is a finite local ring, so therefore I have a sort of maximum ideal M here. And I can pull it back. I mean, the residue of the maximum ideal is going to be some sort of finite field. So I will get something pulled back. I don't know why my reference says CF. It's a term of notation. So this is the maximum ideal. I'm going to leave this as an exercise. Every maximum slash prime ideal. Oh, I guess for this, both are right. And also, I want to say that this R, by local, so this is the maximum ideal. I can take the localization. So this is a write a ring and a maximum ideal. It's localization. I'm not taking any completion or anything, just plain localization. I don't have time to prove, I guess. I did write down the proof in the notes. But I think it's a really fun exercise to work with, to play with ultrafilter. So I'll stop here, and next lecture I'll finish the proof.